Hi, I'm Russ Baker. We're going to talk about the concept of logarithms and their properties today. First, let's see what the definition of a logarithm is. If a to the k power equals x, then k equals the logarithm base a of x. A, k, and x are positive. A is not equal to 1. We call x the argument of the logarithm, and a is called the base. The reason we have used this is we need an expression that will allow us to write an equation that solves for a variable in an exponent. The first skill you really have to master with logarithms is conversion from exponential form into logarithmic form and back again. Let's practice. Here's 3 to the 4th power equals 81. If we're going to put this into logarithmic form, we know that the base is still going to be called the base, and so we'll write log base 3. The argument is here, 81 equals the exponent 4. From this we can understand that the logarithm, base 3 of 81, is 4. And so we get a very important idea right off the top that logarithms are exponents. That little phrase will help you with your conversions. Now let's see what we can do with this conversion idea by trying to evaluate a logarithm by putting it back into exponential form. Here's our problem. Log base 4 of the cube root of 4 divided by 2. Now, if we're going to put this in exponential form, we would probably put an x out here like that. Now we can change it back into exponential form. The base is 4. The logarithm is the exponent, x, equals the argument, cube root of 4 over 2, like so. Now the advantage we have in this special problem is that these numbers are all powers of 2. So we could write this as 2 squared to the x power. We could write this as the cube root of 4 is 2 squared, and the cube root is the 1/3 power. So that's 2 to the 2/3 power divided by 2. Now we could simplify our exponents. We can say that 2 to the 2x power is, now we're going to do 2 to the 2/3 power minus 1, because when we're dividing powers we subtract exponents, and so this will become 2 to the 2/3 minus 1, which is negative 1/3. We now see that if 2 to the 2x power is 2 to the negative 1/3 power, well, then 2x must be negative 1/3. Dividing both sides by 2, we would find that x, remember x is the evaluation of our logarithm, is negative 1/6. And that's the solution. Logarithms come in all bases. We can see that from our work with converting for exponents, but there are some common bases that are used more than others. Common logs have a base 10. Whenever we're using base 10 logs, we frequently will omit the base number and just write log. So if you ever see that log, you may assume that the base is 10. There's a log key on your calculator. The other common base that's used is called a natural log. It has base e. The way we express that is to write ln of x. Instead of log base e, we write ln of x. And there's also an ln, or natural log key, on your calculator. Let's see how we could use our calculator to evaluate the logarithm, base 10, of 28 to the third power, or the logarithm of 28 to the third power in natural logs. We'll move over to our graphing calculator and turn it on. And we'll push the log button first. That means we're doing a base 10 log of 28 raised to the third power. And we see that the answer is 4.34 with irrational numbered decimal places after that. Let's try the natural log of 28 raised to the third power. And we see that it will be a different value because it's based on a different number, 9.9966, and so on. Logarithms have many properties, all of which you should become familiar with. Let's look at some beginning ones, see what we can learn from them. Here are the first three properties of logarithms that you should know. If a is larger than 0 and a is not 1, then the log base a of 1 equals 0. That's saying that any base, the log of 1 is 0. Here's another important property. The log base a of a to some power is that exponent. Log base a of a to the k equals k. Also, if you have a to the log base a of k power, that is also equal to k if k is larger than 0. Now let's look at three other properties. Let's assume that x is larger than 0, y is larger than 0, and a is larger than 0 but not 1, and any real number r. These properties are respectively called the multiplication property, division property, and power property. Let's look at them. Log base a of the product of two numbers is equal to the logarithm, same base, of the first factor plus the logarithm base a of the second factor. The logarithm of a product is the sum of the logarithm of the numbers. In a similar fashion, the log of a quotient is the difference of the log of the two numbers. And finally, the power rule is that the log of any base of x to the r power is that exponent times the log of the base. Let's see how we could use these problems to simplify expressions that are written in logarithmic form. We have log base 5 of 5 times the square root of 7 divided by 3. All of our problem will involve log base 5. Log base 5. Here's a product, 5 times the square root of 7. So that means we're going to add the logarithms of those two numbers, 5 plus log base 5 of the square root of 7. And then we divide. When we divide, we subtract the logarithms. So we'll subtract log base 5 of 3. We're not done yet. The log base 5 of 5, that's a simple property that says, oh, well, the log base 5 of 5 is 1. Let's continue. Log base 5 of the square root of 7. We know that the square root of 7 is really the half power. And so we can use the power property and say, well, that's really 1/2 log base 5 of 7 minus log base 5 of 3. And there we've expanded the logarithm of an expression by using the log properties into this larger expression. Now it's time for you to try one. Use the logarithm properties to expand and simplify the log base m of the square root of 5r cubed divided by z to the 5th. Turn off the tape to do your work and turn it back on to see the results. let's see how you did. Let's see now. We have the square root, which is the 1/2 power. We have a log base m. The square root is the half power, so the whole thing is 1/2 power. Let's put that 1/2 out there. And we'll now have 5r cubed over z to the 5th. Now we'll do the same as we did before with our first example. We have 1/2. We're going to put parentheses around this. I hope you remember to do that. And write log base m of 5 plus 3 log m of r, because that was r cubed, and we can use that property, minus, because that's division for z, and we have the 5th power, so we're going to write 5 log base m of z, and we'll close our brackets like that. Remember, when you're taking the square root or any power of an expression, the power, the exponent will come out, and you'll need brackets. I hope you got that one. Now we're going to look at some problems which use the properties in reverse. So we're going to give you the problem and expect you to put it back together. Here's our example. We have 2 log m of a minus 3 log m of b squared. We might do this in 2 steps. First, we notice that 2 log m of a is going to be the log of base m of a squared. And then this 3 will become the exponent, so it's minus log base m of b squared cubed. We'll simplify that in a moment. Now we know that we have 2 logarithms subtracted, and when we're subtracting logarithms, we know that means we're dividing the numbers. Log base m, a squared is the numerator, and b squared cubed is b to the 6th power, and so we end up with b to the 6th in the denominator. Our final solution then is log base m of a squared over b to the 6th, and we're done. Although we use the bases of 10 and e a lot, sometimes we need to change bases from one form to another. We do this a lot when we need to use them with our calculators, since our calculators can only do base 10 and base e. Here's the change of base rule. It says for any positive real numbers x, a and b, a is not 1, b is not 1, the log base a of x, that's our old base, is equal to the log base b, new base, of x divided by the log base b of a. What was a? A was our old base. Well, this turns out to be a very handy idea, because if we were looking for log base 15 of 5, our calculator can't do this, and unless we had some paper tables that told us what base 15 logs were, we wouldn't be able to do this problem. But thanks to the change of base rule, we can say this is the log of 5 divided by the log of 15. We could just as easily have used natural logs ln instead. Let's go over to our calculator and put these values in and see what the log base 15 of 5 actually turns out to be. We'll go over to our graphing calculator, and we'll put in log of 5, close those parentheses, divided by the log of 15, close the parentheses. And we see that the answer comes out to be 0.594, etc., etc. So now we see how we can make those problem sets with different bases still be able to be solved with our calculator. Remember now, logarithms are exponents. Our notation is used for logarithms, helps us solve equations with variables in exponents. The most common bases in use for logarithms are 10, called common logs, and E called natural logs. We can use properties to master in both directions to simplify or expand the logarithm of an expression. You should practice until you're comfortable evaluating both expressions in both directions by applying the properties and using the change of base rule so that your calculator will become an effective tool.